Everyone. So for today, I'm going to present to you our algorithm, which is the round robin scheduling algorithm. So we will explore the intricacies of this algorithm, its applications, strengths, limitations, and a real life simulation to illustrate its practical utility. So, the round robin scheduling algorithm is a fundamental in computer science, particularly in operating systems for CPU scheduling. So, it is known for its simplicity and fairness in time sharing environments. So, the algorithm assigns a fixed time slice to each process and in the ready queue, ensuring equal CPU access. So, this prevents any single process from monopolizing the CPU, which is crucial in multi-users and real-time systems. So the time quantum is a critical parameter in round robin scheduling because it is too small. The system spends more time on context switching than on actual process execution. That's leading to overhead. So conversely, a large quantum can cause longer response times, making the system less responsive. So the key is to find a balance, which often depends on the specific requirements and workload of the system. So in our algorithm overview, the algorithm operates in a cyclic manner. So each process is assigned a time quantum and is allowed to execute for that duration. So if the process doesn't complete within the quantum, it's prompted and moved to the back of the queue. So this ensures that all processes get a fair chance to execute, promoting system responsiveness and fairness. So to help you understand this concept better, so imagine a household where chores are rotated among family members. So each person gets a fixed amount of time to complete their task before moving on to the next person. So this rotation ensures that chores are distributed fairly and no one is overburned, much like how round robin scheduling ensures fair CPU time allocation. So here in our pseudocode, we have here a pseudocode for household chores simulation. So as you can see in our pseudocode, this outlines the basic steps of the round robin algorithm applied to our household chore simulation. So, we start by initializing a queue to hold all the family members and set a fixed time quantum for each chore. We then dequeue the first family member, assign a chore, and allow them to perform the core for the time quantum. So if the core is completed within that time, we mark it as a completed. Otherwise, we in-queue the family member back to the end of the queue to continue the core in the next cycle. So we also handle new cores arriving by adding them to the queue.
So now let's discuss the time complexity of Rand-Rubin algorithm. The time complexity of Rand-Rubin is big O of n times burst time over Q, where n is the number of processes or family members in our simulation. Burst time is the CPU time required by a process or the time required to complete a core, and Q is the time quantum. This complexity highlights the trade-off between the number of processes and the quantum size. Smaller quanta increase the overdue due to more frequent context switches or interruptions in our simulation. This linear relationship means that as the number of processes or the burst time increases, the total execution time also increases. However, the algorithm's fairness and responsiveness often justify this trade-off, especially in systems where equitable resource distribution is a priority. The overhead from the context switching can be significant if the time quantum is too small, but it ensures that all processes get a fair share of CPU time. In practical terms, the time complexity implies that the algorithm scales linearly with the number of processes in the CPU requirements. This makes round-robin particularly suitable for systems where fairness and responsiveness are critical. However, it's essential to carefully select the time quantum to balance between minimizing context, switch overhead, and ensuring timely process execution.
So we conducted a simulation using a household chores rotating scenario. So each family member represents a process and each process represents a task. So the time quantum is the fixed duration each member gets to perform their chores before rotating to the next member. So we tested scenarios with equal workloads, variable task durations, interruptions, and adding new tasks so that the simulation showed that round robin effectively distributes the workload fairly, handles tasks requiring multiple cycles, and adapts the interruptions and new tasks without causing delays or starvation.
Household chores made fair. Round robin scheduling in action. Ever wonder how computer algorithms can help with chores? Let's dive into the round robin scheduling applied in real life. Meet our crew. Alice with 30 minutes of chores, Bob with 15, and Charlie has 20 minutes ready to tackle. We'll rotate their work in 15-minute slices. Alice, Bob, and Charlie get a fair shot. No one hogs the chores. First up, Alice. She starts with the dishes. Ready, set, go. 15 minutes later, Alice has done half her chores, 15 minutes left to go. Nice pace, Alice. Up next, Bob jumps in and tackles vacuuming. Full 15 minutes, focused and efficient. Bob wraps it up perfectly. All chores done in one go. That's how you keep it tight. Now Charlie steps in for laundry duty. He works 15 minutes and still has 5 left. Almost there. Back to Alice for round 2. She finishes all her chores with another focused 15 minutes. Last push for Charlie, 5 minutes to finish laundry. He's done. Everyone's chores are complete. Let's glance at the finish line. Alice at 30 minutes, Bob at 15, Charlie at 35. Fair and square. Alice says, "It feels fair and balanced." Bob agrees, "Efficient and stress-free." Charlie adds, "Rotation made it so manageable." This is round-robin scheduling. Dividing time fairly keeps tasks smooth, fair, and easy to handle.
Now, let's evaluate the performance of the round-robin algorithm. We focus on metrics like average waiting time, turnaround time, and CPU utilization. Round-robin performs well in ensuring fairness and responsiveness, but the overhead from the context switching can be drawback if the time quantum is too small. Compared to the algorithms like first come first serve or FCFS and shortest job first or SGF, round robin offers better fairness and responsiveness. However, it may not be efficient in minimizing average waiting time as priority-based algorithms. The choice of algorithm depends on the system's specific requirements.
Finally, let's discuss the strengths and limitations of the round-robin algorithm. The algorithm's strengths lie in its fairness and simplicity. It ensures that no process is starved of CPU time, make it ideal for time-sharing system. However, the choice of time quantum is crucial, and the algorithm doesn't consider process priorities, which can be a limitation in some scenarios.